Hello everyone and welcome back to AMOS, our course on Agile methods and open source. We are smack in the middle of discussing Scrum and now Agile software development, which will actually add to a couple of process practices from Scrum, now programming principles, engineering practices of mostly the extreme programming space. Basically, in addition to the core Scrum, there are an array, a host of different techniques and principles and practices of how to build systems that have made it into mainstream. Some, not all of them, originally from extreme programming, and they also are an important part of Agile software development to be discussed here. So let's start with the role of the software developer, which actually in Scrum terminology is a team. With Scrum 2020, the team, just the team, became the software developer and the PO, the product owner, sometimes also the Scrum Master. So everyone involved, every committed person to a project or product development. Now, within that, there's the software development team, because that's the largest number of people, because there's usually one PO, one Scrum Master, and then there are 5 to 7 in one team, software developers. Their job is, as you know, the overall responsibility. Their job is to make sure that there is useful software at any point in time or at any incremental delivery moment, meaning sprint release at the end of each sprint. And so they take care of that. The interesting thing about a software developer in Scrum is how they combine these different aspects from the traditional business functions of software development. They are both engineering managers, they're all engineering managers, software developers, and even to quite an extent take over quality assurance, which traditionally was that separate department that did not have a conflict of interest with the actual developers, so that it could provide that thorough independent assessment of whether you could release, say, a product to a market. And so all of that in Scrum maps into this one role of a software developer. Every software developer is an engineering manager, software developer, and even quality engineer. So the role of a software developer in sprint planning, of course, is, as we discussed, in the estimation, the planning poker game, helping the product owner and defining how much work is to be done, and so forth. And in addition to agreeing on the sprint backlog for a sprint, there's additional work for software developers to be done. In the AMOS project, we don't make it a part of the team meeting, but it can follow on right after the team meeting, because once you have settled on a sprint backlog and committed to it, the entries in the sprint backlog, the features to be done, may still be too big, too coarse. At least in industry they often are, because that's how a typical product owner may think about it. In AMOS, we kind of assume that the product owner can break down features, product backlog entries, and sprint backlog entries into sufficiently a small size so that there is very clearly a one-to-one mapping between a feature, the implementation work to be done, and a single person or a pair of developers who does it. But if features are larger, and that works for the team in industry, for example, then there is an additional step after agreeing to a sprint backlog, which is that each sprint backlog entry, each feature or refactoring or what have you inside the sprint backlog, still needs to be broken down into tasks that might possibly be done by different people. In AMOS, it's unlikely because we expect the POs to be sufficiently technical, and given the sprint duration of sprint length of 1 week, it would be the features will always usually be so small that they have to be close to ultimately the engineering tasks behind it. And so developers nevertheless have to sometimes break down more complex features into tasks after or at the end of the sprint planning meeting in industry, not in AMOS. And for that, they need the feature, task board, and so forth. And then their job is to implement it, the feature or the tasks for the feature. And they can track that using, again, a task board like we're using it in AMOS. So here is the GitHub project, which is a weird name for a Kanban board. That's or just a task board. That's the more common name. And we can see how the columns in the task board have been adjusted to the Scrum terminology of a product backlog on the left, with all the outstanding work, the sprint backlog being the work that the team committed to for the current sprint, in progress, what developers are currently working on, and awaiting review, the work that they have finished but have not yet reviewed in a review meeting. So awaiting review means that it's been done, or the developer believes it has been done, but it is still pending the review. And if it passes review, it gets moved into the feature archive. If not, it's moved back into the product backlog as discussed before. So that's the task board or Kanban board, visualizes the progress towards finishing this current sprint and also shows what's coming up perhaps in the next sprint. As you work with such a task board, by now, please do not forget your definition of done. You should have a definition of done by now, and you should apply it consistently to features, sprint releases, and also soon a project release. Here is some fun cartoon where if you're sloppy on definition of done and it's almost done, you can be so much faster. But then maybe you also have to redo a lot of work, or it's just not, this code just does not meet your quality criteria. So beyond the basic, here are features. Let's break them down into tasks. Let's get chugging. Let's get working on those tasks, which has a scope of the sprint. You also can and have to look at the work of a single day, at least in industry. So day planning simply means that you meet in the morning, usually, whether virtually or in person, and perform a so-called daily Scrum or daily stand-up. That's synonyms. And the whole point is to coordinate each other, to give everyone else a very short insight into what you did yesterday, what you're going to do today, and what potential problems are. So it serves coordination purposes. It does not solve problem-solving purposes. So it's only to inform people, and if there are recognizable problems that people talk about, then they are impediments, and if they are urgent and can't wait for the retrospective, then the Scrum Master may have to pick them up, but they are picked up after the daily Scrum, because as before, you do not want to keep everyone listening to some problem resolution discussion which really only matters, say, to two people. So that's why everyone needs to know a problem, but they don't need to sit idle by and watch while someone else is solving it. So you take it out of the meeting and solve the problems afterwards. Here is how pre-corona physically you could possibly meet. You usually stand in a circle and do the roll call, which really then is a circular call on what did you do, what problems were there, or are you expecting, and what are you going to do. So that's the daily Scrum, a daily synchronization meeting by the committed people. You can poke fun at it if you think it takes too long because people want to discuss their problems rather than just inform everyone about it. Then the product owner or the developers themselves can decide we make it a plank meeting so that there's clear incentive to not talk too long. Now on from process practices to the engineering practices, the extreme programming and general principles of Agile software development. The Agile folks were pretty good at giving us cute acronyms. This one's actually general, doesn't really just relate to Agile, but it's clearly a rallying cry. Try to keep it simple. Meaning, if there are two possible solutions, choose the simpler one, and that will be beneficial to everyone because you are postponing any complexity because you don't need it. That is also expressed in another acronym, YAGNI, you ain't gonna need it, trying to stop people, engineers in particular, who like to do it, to go beyond what's currently necessary by speculating too much about the future. Now, I'm an engineer, we just like to do it, we like to think ahead, we like to build grand architectures, but built into let's design this fabulous system is a lot of assumptions about the future, which may never come true. So when you design a grand architecture, you buy lots of options, so to speak, and many of them will expire without ever being worth anything. So Agile says just keep it simple because all the grand things you're worrying about that might happen, you won't need the problem solutions to those because those worries never take place. Your planning horizon is long term, but you just don't know what's going to happen. So the visibility into the future gets less and less good the further out. So do not plan too much for it. And another nice acronym is DRY, do not repeat yourself. That refers to keeping your code simple. So write simple code. If you find yourself writing the same code or even worse, copy and pasting code, there may be an indicator to something fishy going on. And we will see that in a bit when we talk about refactoring. Here's one that I like to add, mostly about premature optimization. When you think about writing code, you can take it in 3 steps. You decide this is what you need, and you're not going too far into the future. You just want to program something, that's just fine. The way to think about it is in terms of getting there expediently and efficiently is to first make it run. So write code that does what you want it to do in general, and it doesn't have to be perfect code. You want to see it run and that it does the job. And then in a second step, you think about making it right, meaning giving it a good design, cleaning up some poor code and so forth, so that it becomes maintainable. Conceptually, that's different. Step one is understanding the problem. How am I going to solve it? Number 2 is solving it in a good way that other people can understand. So you clean up things so that your understanding becomes understandable for others as well. And then in the third step, sometimes you have to make things fast, so improve performance. And it's important that you don't let this step of working on performance, efficient data structures, efficient algorithms, that you don't pull this forward, that you don't let it interfere with your learning about the problem, which is making it run, and you're expressing an elegant and clean problem solution that's understandable to others, that is, make it right. Any optimization is usually going to make code less readable, so if you don't have to do or take step 3, don't take it. But if you have to take it, then do it at the end. All right, so one interesting aspect with a lot of debate is the question of, are there owners of code or not? The traditional answer usually has been, of course, there are code owners. People like separation of concerns or divide and conquer, all these kind of strategies, where, say, a software system would have different parts and then different people get assigned to work on different parts. That is clearly a good recipe for scaling up. It also means that if you work on part A, you may have no idea how part B or C work. And so you will never, or it will find it hard to fill in for other people. Within the scope of Agile and Scrum, on the level we are talking about it here, meaning teams of 6-7 people, it is understood, or the Scrum authors argue, that you should own the code collectively. Everyone should have access and equal rights and may actually end up changing or evolving all the code. So there is no divide and conquer into different teams. And certainly this can work. So it's called collective code ownership. As a collective, you own the code. And it can work, again, for a project size that requires only one team. Debatably, it might break down right away as soon as you have more than one team, which you will typically establish once you simply need more people and you don't really want to run a 15-people Scrum team. So the purpose is, collective code ownership means everyone has full read and write access, and the purpose is to instill that feeling of overall responsibility for the code base. So if you find poor code in some places, you should not hold back in terms of fixing poor code, because it's not your code and you worry on stepping on somebody's toes. But collective code ownership means everyone's responsible, not only for new code, but also for cleaning up old code, and in general being knowledgeable so that you could possibly work, that's the idea, on every part of the software system. How likely that is, certainly in an AMOS project, in a student project, which has enough complexity to begin with, is maybe not so clear, but that's the basic idea, and that's the request of the original extreme programming developers. So everyone cares, everyone's capable of fixing up everything. There is one particular architectural issue that plays in, which is extreme programming or agile development practices are feature-driven. That means that all the work you do comes from the sprint backlog. There's a feature or refactoring or so, and that is something that you need to implement. And that's not necessarily logically restricted, or it should not be written in such a way to be restricted only to, say, one tier of the architecture. So you should not write user interface features, you should write business-oriented features. And a business-oriented feature will very often cut across all tiers or all layers of a software stack. So all tiers of the runtime architecture and all layers of the code architecture. And that means that you really need to be knowledgeable about all of them if you want to be able to implement a feature end to end. The alternative is to have so-called feature teams, which are also not uncommon in the industry, but at least in theory, according to the Agile, to the extreme programming authors, original developers, you should be basically a full stack programmer who can fix up everything, because only that gives you the business orientation, the focus on the business value from the features of the sprint backlog. Beyond collective code ownership, so an additional supporting element is to simply have a shared programming standard. If you have collective code ownership, you would go crazy if everyone had a different programming style. So you absolutely need to agree on a standard. Usually it comes with the programming language, and it makes sure that you write code that is more easily understandable than if you had no programming standard or coding guidelines, that is more easily understandable because of that standard to your fellow other developer. So having a programming standard supports collective code ownership because it's easier to find your way around other people, the code that other people have written. And it really helps keep clean code, recognize bugs faster, and so forth. And you really should have made it mandatory. Again, such coding guidelines or programming standards often come with the original programming language, though they are not necessarily exhaustive. You should usually stick with established standards, so don't make things differently from what the designers of the original programming language thought would be a good idea. But you do often have to add to it. So here's an example that I teach in my programming courses on the language that professional software developers use, but which has not really been defined. Actually, in my opinion, you could write a book about it, and maybe bits and pieces have been written about it. Most notably, for example, if you're a developer, you most certainly will know what a getter or a setter is. It's a specific type of method. It's very simple. A getter returns a value of an attribute, and a setter sets the value of an attribute. But beyond these two well-known examples, there are many others. So you have conversion methods, initialization methods, logging methods, assertion methods, cloning, factory methods, template methods, and so forth. All of these terms have some definition and will be understandable to the professional software developer what they mean. As a consequence, you can say, oh yeah, this method really is a template method with 3 hook methods for overriding through subclasses. And then you don't have to say so much more because this terminology is understood. And hence, professional software developers, so you will grow into that if you're not already there, and have this added vocabulary beyond the programming standards of the programming language. And yeah, well, you need to develop knowledge of that. It applies on the even more basic level than methods. It applies to how you name attributes, classes, packages. It obviously applies to the methods. It applies to how you structure your packages and how you deal with collaborations, how you group classes into packages, how you create modules from that, how you separate testing and production code, and so forth. Here is a question on Agile software development, testing what we just discussed. A file may have many authors. Absolutely, collective code ownership. Should the names of these authors be listed in the file's header? Yes or no? What do you think? Well, there are a lot of pros and cons. So the first distinction is it open source code or not? Let's assume it's open source code. Then we actually, if you go back to the reuse example, have the recommendation that every copyright holder, if you're an author of in an open source project and you contribute to a file, you hold some of the copyright in it, then you should list yourself as a copyright holder. But that's the legal consequences of being open source. So now let's assume you are a developer inside a company and it's proprietary code. Should you still list your name in the file header? I would argue that version control does the job of helping people identify who contributed. If there's a lot of back and forth, it might be easier to have the names in the file header, but in general, I don't think it's a good idea. If you have collective code ownership, putting your name, putting your stamp onto a file is actually counterproductive because it does have the smell of you brandishing the file as yours, even if that may not be your intention. So I think for closed proprietary code, do not put your names into the file header. So about 20 years ago, 30 years ago, with Bill Opdyke's dissertation in 1991, we came up with the idea of technical debt, and based on that, refactoring. So technical debt is a metaphor to help you deal with bad architecture, bad software architecture. So here you can see a slum that is some sort of architecture. Well, I guess it works better than you sometimes might think, but I'm pretty sure some things don't really work well here. I don't even want to ask about sanitation or safety at night and so forth. So software architectures which look like this have no immediate apparent grand scheme of things helping people orient themselves are often called a big ball of mud. Not very nice, maybe also a little bit of arrogant, but the point here is that these are real world, real system architectures, and they are created over time by slapping on layers of layers, like you create a big ball of mud from smaller balls of mud onto which you add some more mud. And so layer on layer on layer you put on top of it, and there is no really easily understandable structure. It's all somehow intertwined. So maybe the original term of it was spaghetti code. Big ball of mud is just another synonym for that. And you really don't want that. Ideally, if you can avoid it. Not always easy. Why do you want to avoid it? Well, because you want so-called well-factored, well-structured code. Because well-structured code is more maintainable, meaning it's easier to understand, and hence you can change it more easily. It's also more extensible because it's easier to understand. And if it's well factored, it's very clear how to extend it. So if it's easier to understand, you can more easily extend it, which you usually have to do because systems grow. So it's easier to adapt and evolve the software. And finally, if it's well structured and you know what you're doing, you have a higher predictability with respect to what will be the consequences of changing this or that. So you can, at least in your mind, perform some change impact analysis and get a better understanding of, will you get where you want to get, or will there just be a gazillions of bugs and problems in your way? So with higher predictability comes higher planning ability, all the things about development speed, equal level of quality, and predicting your burn downs, all of that becomes possible if you have good well-factored code, and becomes questionable if you don't. So let me look at technical debt from the perspective of the person who coined the term, Ward Cunningham.
I became interested in the way metaphors influence how we think after reading George Lakoff and Mark Johnson's Metaphors We Live By. An important idea is that we reason by analogy with the metaphors that have entered our language. I coined the debt metaphor to explain the refactoring that we were doing on the YCache product. This was an early product done in Digitalk Smalltalk, and it was important to me that we accumulate the learnings we did about the application over time by modifying the program to look as if it had been as if we had known what we were doing all along, and to look as if it had been easy to do in Smalltalk. The explanation I gave to my boss, and this was financial software, was a financial analogy I called the debt metaphor, and that said that if we failed to make our program align with what we then understood to be the proper way to think about our financial objects, then then we were going to continually stumble over that disagreement, and that would slow us down, which is like paying interest on a loan. With borrowed money, you can do something sooner than you might otherwise, but then until you pay back that money, you'll be paying interest. I thought borrowing money was a good idea. I thought that rushing software out the door to get some experience with it was a good idea, but that of course you would eventually go back, and as you learn things about that software, you would repay that loan by refactoring the program to reflect your experience as you acquired it. I think that there were plenty of cases where people would rush software out the door and learn things, but never put that learning back into the program, and that by analogy was borrowing money, thinking that you never had to pay it back. Of course, if you do that, say with your credit card, eventually all your income goes to interest and your purchasing power goes to zero. By the same token, if you develop a program for a long period of time by only adding features and never reorganizing it to reflect your understanding of those features, then eventually that program simply does not contain any understanding, and all efforts to work on it take longer and longer. In other words, the interest is total. You'll make zero progress. A lot of bloggers, at least, have explained the debt metaphor and confused it, I think, with the idea that you could write code poorly with the intention of doing a good job later, and thinking that was the primary source of debt. I'm never in favor of writing code poorly, but I am in favor of writing code to reflect your current understanding of a problem, even if that understanding is partial. If you want to be able to go into debt that way by developing software that you don't completely understand, you're wise to make that software reflect your understanding as best you can, so that when it does come time to refactor, it's clear what you were thinking when you wrote it, and making it easier to refactor it into what your current thinking is now. In other words, the whole debt metaphor, or let's say the ability to pay back debt and make the debt metaphor work for your advantage, depends upon you writing code that is clean enough to be able to refactor as you come to understand your problem. I think that's a good methodology. It's at the heart of extreme programming. The debt metaphor is an explanation, one of many explanations of why extreme programming works.
All right, so this was Ward Cunningham, one of the three inventors of extreme programming, next to Ken Beck and Ron Jeffries. So I really liked his point about programming to learn. When you're programming, you're problem solving, you're growing your understanding of the problem and how to solve it. It's also worth noting that the technical debt metaphor speaks particularly well to managers, because everyone, in particular these managers, are not really software engineers and don't really have a good understanding of what happens when you write code and you're developing software, which is a still very common problem. And everyone understands the financial domain, so that is an interesting analogy. It easily gets carried too far, because naturally managers in large companies will want you to qualify your technical debt in euros. So how much time will it cost you to fix all of this into perfect quality code? And that, I think, is the wrong way to go about it. Still, you can communicate to your managers that maybe if you're forced to write code to get some work done but never get the time to fix it up, that you're accumulating, as explained by Ward, that you're accumulating debt that you'll have to pay back. I think it's strong to realize that there's interest if you have too much debt, and that this interest can weigh you down, meaning poor code quality can weigh you down so much so that your development comes to a screeching halt because you will not be able to write new business value features if all you do is stumble from one bug to the next, which is why you need that balance of fixing bugs and moving the project along by writing new functionality. So to handle technical debt, so you can incur it, but then you also should pay it back. To handle technical debt, you first need to identify the problem. Even if you're programming and you think it's not quite clean, maybe you don't even realize that you were just creating or taking on technical debt. So there needs to be identifying things called code smells in a few seconds. So if you have code smells, they indicate to you that there are problems, and that might be technical debt. So as you look at the smelly code, then you should see whether there's a need to act. You don't necessarily, just because something stinks doesn't mean you have to kick into action right away. Maybe there are smarter ways of dealing with it. Maybe it's an irrelevant problem. And once you identify or learn or realize that you actually have to do something about it, then of course the question is, how do you go about it? And these are the 3 key steps which we will discuss now, because they have been not formalized, but have been buttressed with a lot of practical knowledge and practices. So first, code smells, identifying technical debt or just poor code quality. So a code smell is structures in your code that somehow violate what you should have come to know with growing experience as good design principles. For example, separation of concerns, or having good cohesion, having coupling or only loose coupling between highly cohesive modules, and so forth. So these principles, as they get violated, are smelly, or give you code smells, or are code smells, and then typically indicate deeper problems in the system. Code smells are not bugs. Bugs are simply mistakes where business functionality is not calculated or performed correctly. Code smells might very well do their job, which is why it can be hard towards a manager to argue you want to remove a code smell, because they say, what are you complaining about? The code does its job correctly, so no need to clean it up. Well, you may have to clean it up if it gets too much. Code smells, here's some example. Copy and paste. Yeah, so someone copy and pasted like crazy. Obviously, perhaps it should have been put into a more general method rather than duplicating your code. Long methods suggest you don't understand the problem. Your understanding of the problem, hopefully deep understanding of the problem, has not been expressed sufficiently well. Large classes, so not well-factored code. Not well-factored code means maybe you should get it to be well-factored, and you do that by the so-called process of refactoring. So refactoring, by definition, is a behavior-preserving transformation of existing code. So again, your assumption is smelly code, but it's not a bug. And refactoring of such code then is changing the code structure, moving it around, but never actually change the actual behavior. So from the user of a system, from the user's perspective, nothing actually changed. It's the internal workings that got more efficient, but in terms of business functionality, there is no need. There's nothing that has changed. But the system got slimmer, and from the developer's perspective, who is a stakeholder, it got better now. The Refactoring is about 30 years old. It was popularized about 20 years ago by Fowler in a book on refactoring, which gives you various strategies of not only how to identify things that are wrong, this was the previous step, code smells, but then how to perform the cleanup. And so they have all names. These are patterns or refactorings, if you will. You might have to rename a class if it has a poor name. You might have to pull a method out of redundant code. You may have to pull up a field in a class hierarchy, etc. The refactoring.com website gives a nice overview of some of them. Here's a simple example. Marked in bold is a direct manipulation of some map, the all photos map from the Wildsight application, and maybe this particular map should be hidden behind a getter or setter or a putter in this case perhaps. So you should factor out this change of an important instance field, should factor it into its own method. So it's extract method into do add photo, which is called from the places where it is needed. Developers are, of course, prone to carrying, like everyone, carrying to their own needs first, meaning having really nice, clean code, which may be not necessarily in the economic interest of the overall project. So how do you avoid getting overzealous, overly eager to refactor? Well, here is the 3 strikes rule, which is a good indicator or trigger for when you should refactor and when you should hold off and not yet refactor. So the 3 strikes rule goes like this. You write code the first time, you just do it. And you make it run. And as you write code that's somehow similar, for example, or where you identify the same problem, but it's only the second time you notice, but you don't necessarily act. So if you write code, for example, same code for a second time, that's not yet a reason to do anything about it. Only if it's there for a third time. If you find yourself writing the same code for the third time, then you should refactor. And that means if it was just duplicate code, you extract it into a method. This holding off until there is a third time and not just do it at the second time is, of course, a variant of the agony of you ain't gonna need it. Don't overly eagerly refactor. Wait until you have better data that a refactoring actually makes sense. Logically, as you do that, you switch between 2 states while you're programming. So in one state, you are programming code. You are in the add functionality, add function state on the left, and you keep chugging along and you write code, and that's great. Eventually, some code smell becomes too strong. So maybe the third time you notice you write the same code. Then you should finish your add function task and switch hats or switch into the second state, the refactoring state. In the refactoring state, you're not adding new functionality. You're not changing the behavior of the system from a business function perspective, but rather you're improving and you're changing the structure. You're refactoring. You're performing a behavior preserving transformation until the smell goes away. Once you have finished said refactoring, then, and it's not smelly any longer, you leave the refactoring state and go back to add function. These 2 states of work arguably are semantically closed. And for example, if you're a good programmer, it means they're separate commits, because commits should be semantically closed. You don't do several things in one commit. You map one task, like add a new function, to one commit, and you add another task, like refactoring something, that becomes a third commit. So you keep these things separate. You're very clear in your mind where you are, and you don't mix them. The smells lead to refactoring. So when you look at the refactoring book, you can see a mapping between code smells, triggers, for triggers or need for action, and the corresponding solution, what to do, how to act, on the right in the form of refactoring. So duplicated code often leads to extract method. Might also lead to pull up a field in the class hierarchy or form a template method. So this way, when you identify a certain smell and you're not sure what's the best course of action, you can actually even consult the book and look at what are common actions to remedy, to remove the smell. In practice, such refactorings can become complex, as a code smell may require multiple refactorings to resolve the smell. And so that's why it's good to be fluent at these refactorings. You understand that you first have to extract a method, and then you may have to move it inside the class hierarchy and so forth. And maybe inside the method you will have to go from switch case statements with type codes to polymorphism, dispatching in different ways, and so forth. So there are many different ways of how refactorings are changed. Like before, each individual step should be self-contained, probably its own commit, semantically closed, so that each commit really uniquely does one thing and one thing well, which makes it easier and better for others to understand what you did. Refactorings have become so popular that you have them as functions in your IDE. So you can choose a menu item to perform some code manipulation, meaning the behavior preserving transformation. But realistically, when you look at how people use these tools, the one thing everyone uses is rename. So that's key. You rename a method or you rename a class, you know it needs to change in many different places consistently. It's a nice help if you don't have to go to all these places by hand, but just call up the context menu on one occurrence of the name and there click on rename, and then consistently it gets changed anywhere else. I think that's 80%, maybe it's 95% of all refactorings performed through IDE functionality. And I would argue, I suspect the reason is that rename is clearly, easily defined. You trust your IDE to get the rename right. While if you do extract method, that's for example possible here, or even extract superclass, how can you feel sure that these tools don't make a mess out of your code base? Well, the tools have been programmed to not make a mess, but most developers I know still wouldn't trust it to do it well. So then, here's a short quiz. Your code smells, well, some of it. All signs for refactoring are given. When should you not start a refactoring? Are there situations where you should not refactor your code? What do you think? Well, I guess there might be special situations where refactorings won't add much value, most notably if the component you are working on gets abandoned, has no business value any longer. So if the work you put in for refactoring is not going to pay any dividends because, well, the code is going to be abandoned, then maybe the refactoring is not necessary. Also, you may have to reprioritize. So some refactorings may be more important than others, and yours may just not be that important, and the product owner will keep it down, further down in the product backlog. So with that, we talked about some of the process practices from Scrum for Agile software development, and then switched to the programming principles, the engineering practices, mostly coming from extreme programming, code ownership, technical debt, and refactoring. Next time, we will then talk about test-driven development as another step in this chain of practices that make you an Agile developer. With that, thank you very much for your time and attention, and see you in the next session.